Exercise 73. In this one, we are given two things actually. The first one is this subset of the group S4, the symmetric group of degree 4, and the subset consists of all the squares of the elements of S4. And a similar one K is also given for S5. We have to prove that this H is actually equal to the alternating group of degree 4 consisting of all even permutations in S4, and like that K is equal to the alternating group of degree 5. So let's see the solution. Since every element of H is an even permutation, we have this containment that H is contained in A4. But why is it so? Why is it the case that every element in H is an even permutation? Is being square equivalent to being an even permutation? Well, evenness is a consequence of being square. Within brackets, we can roughly demonstrate that fact like this. For any alpha belonging to S4, if alpha is equal to, okay, so we already know one fact about any permutation, that any permutation is a product of transpositions, that is two cycles. So if this alpha is a product of these two cycles, say A1, B1, A2, B2, AN, BN, then what is alpha square? Alpha square is just this product followed by another such product, that is and then again this is one alpha, another alpha. So how many cycles are involved, how many two cycles are involved in this product? 2n number of two cycles, and that number is even, so that's why alpha square belongs to A4, it's an even permutation. Regardless of what alpha is, alpha itself may be an odd permutation, but that does not matter. So this belongs to A4, and that is why H is contained in A4. Now we want to show that the reverse inclusion is also true, and for that we have to prove that every even permutation in S4, in other words, every element in A4 is in H, that is every element is the square of something in S4. So for that we are now going to look at all the elements of A4 and see that each one of them is a square of some element in S4. But this of course we need not do for each element literally, but we are going to look at the types of elements that we have in A4. Namely, by type I mean the cycle structure. For example, in A4 there are some elements which are products of two disjoint two cycles. So it's enough to consider any one of them, or in fact we need not actually consider a concrete such element, say 1 comma 2 times 3 comma 4, but a general one, say a comma b times c comma d. So we are going to concentrate on the cycle structures themselves. Now the identity element of course is a square, it's the square of itself, and that is E is the identity permutation, which is equal to E square. Then next comes this cycle type, which is a product of two disjoint two cycles, and for that we need these symbols A, B, C and D to be distinct, 4 distinct symbols, and you already know that these are going to be the numbers 1, 2, 3 and 4 in some order, okay, in some arrangement. Now this is one such element, a general such element in A4 which looks like this, and actually there are precisely 3 elements in A4 of this form. One of them is 1 comma 2 times 3 comma 4, then 1 comma 3 times 2 comma 4, and one more 1 comma 4 times 2 comma 3. So this represents any one of them, and this, it turns out, is equal to, let me see if I have got it correctly or not. Okay, I think I need to change the order. It's not just simply A, B, C, D, but rather A, C, B, D square. Let's see. If we apply this square to the symbol, I mean this square is after all a permutation, no, it's a function. If I apply that on the symbol A, what do I get? That means I have to apply this 4 cycle 2 times because we have square. So once I apply it on A, I get C, and then on C again I apply the 4 cycle, I get B. So that means this square takes A to B, A goes to B. Okay, what does it do to B? B goes to D and D goes to A, so B goes to A, fine. C to B, B to D, so C goes to D, okay, and then D goes to A in one application, and then in the next application that A goes to C, so D goes to C, yes. And then there is another cycle type, that is the 3 cycles that are there in A4. So we can just simply consider an arbitrary one, say A comma B comma C, and it turns out that this is also a square, the square of this. Here also let's verify. A to C, C to B, that means A to B. B to A to C, so B to C. C to B, B to A, so C to A. Yes, and that's just it. Where A, B, C and D, of course, are coming from our set 1, 2, 3, 4, and they are distinct. Are distinct elements in our set of symbols on which actually we are considering all these permutations or mappings. So that's it. This shows that A4 is also contained in H. So now you combine these two containments, thus H is equal to A4. And a similar argument will give you the other claim that K is equal to A5. One can similarly show that K is equal to A5. In fact, I want you to actually do this, this second thing. So there the solution ends. Let's now see the next one. So for S4, it turns out that the square of all the elements, it gives us A4, the alternating group, all the even permutations. For S5 also that is happening, but in S6 that does not happen. So that is the next problem. Exercise 74. Let, like before, let H be the set of the squares of the elements in the symmetric group S6. But in this case, H is not equal to A6. Prove H is not equal to A6. Note, we already know one thing from the previous solution, that because we are considering squares, H will be a subset of A6. That's because no matter how many cycles alpha has, that is how many cycles there are in a representation of alpha as a product of two cycles, because you are considering square, so ultimately the square will have an even number of cycles, and as such any alpha square is, simply because it is a square, is an even permutation. So H is going to be a subset of A6. However, the converse will not be true. So for that we need to come up with an element in A6 that is not a square. So because we are not dealing with real numbers but rather permutations, so saying that a given permutation is not a square requires us to know what squares are actually in S6. When we take the square of any element in S6, what do we get? So what we are going to do in the solution, in the beginning of the solution, is that we are going to take the squares of all the cycle types and then see what we are getting, and from that information we will be able to in fact choose an element in S6 which cannot be any of those squares. So that's how we are going to proceed. So let's see the solution. Because we are going to consider arbitrary element of S6, so at the outset let's choose the symbols. Let A, B, C, D, let me take F and G, because by E I am denoting the identity permutation. In the text, however, the author is using epsilon. You can use any symbol you want. B, distinct elements in the set of symbols that you on which you are considering the permutations in S6. You have all the permutations which are permutations of these symbols. Now the square of the identity is of course identity, that's just it. And then we have so many different types of cycle structures, right? For example, to start with, we have just a single 2 cycle, a transposition. Its square is going to be again identity, because we already know this, or you can calculate if you want. A goes to B and then B again comes back to A. So A is unchanged. Just like that, B goes to A and then again that A goes back to B. So B is also unchanged. That means this square does not affect the symbols or does not change the symbols A and B. And of course it does not change the other symbols also, which are not A and B, simply because they do not appear here. So that means it does not change any symbol, and that's why it is the identity permutation. Okay, next we have 3 cycles. If we consider the square of a 3 cycle, then from the previous calculation, you are just going to, or you can in fact actually calculate it, and you will get A, C, B. Next, we have a 4 cycle, the square of a 4 cycle. So this we need to calculate, and we can do it rather fast. A to B, B to C. So A goes to C. C to D, D to A. So C comes back to A. Then what does it do to B? B to C, C to D. So B to D. And then D should come back to B. Let's actually verify that. D to A, A to B. So D to B. Yes. So this is another square. In fact, this is what we previously also got, right? That any product of 2 disjoint 2 cycles is a square. Here we are going the other way. And then there are other cycle structures. So 2 cycle, 3 cycle, 4 cycle, and let us now consider a 5 cycle. Now what happens to this? So first let's see what happens to A. A to B, B to C, that means A to C, just like before. Okay. But now C to D, D to F, so C goes to F. F to A to B, so F goes to B. B to C, C to D, so B goes to D. I have to write it this way. It looks, it doesn't look good, but what can I do? And now where does D go? D goes to F when you apply this 5 cycle once, and then when again you apply that, F goes to A, so D goes back to A. So the square of a 5 cycle is again another 5 cycle. Next. What else do we have? We are all, of course, going to have a 6 cycle, but we are going to consider a 6 cycle afterwards. But before that, we also have this cycle structure, a product of 2 cycles, one of which is a 3 cycle and the other one is a 2 cycle, and they are disjoint. Okay, now you can apply a trick here in calculating this square. that this square will be equal to this square times this square. Why? That is because if you just simply write the square by writing the element next to itself, that is ABCDF and then again ABCDF, but then disjoint cycles commute, and that's why in ABCDF you can make the middle two commute with each other. That way you will get ABC square DF square. But we already know that the square of this two cycle is identity, which will just simply vanish, and the square of this one is ACB. Next you have the square of a product of 3 two cycles. And like above, here everything will vanish actually. These 3 two cycles also commute with one another, so the square will get, the 2 will get distributed over these factors, and each of these squares equals E, and so the entire thing equals E identity. Then we also have the product of a 4 cycle and a 2 cycle, and disjoint of course. Again, just like above, and we already have this square, so we can just simply write AC. This is going to vanish, ACBT. Next, a product of 2 3 cycles, ABC times DFG. Here also we can use that disjointness of the cycles and hence the fact that they commute to have ABC square and DFG square. I hope I can get the job done within this space. ABC square DFG square. ABC square is ACB. Similarly, DFG square is DGF. The last two get switched. They switch places. And then finally we have the square of a 6 cycle. This is going to be, it's better I write it in the next line. A goes to B, B goes to C, so A to C, okay. C to D, D to F, so C to F. F to G, G to A, so F comes back to A. We get 1 3 cycle, and this 3 cycle has missed the symbol B. So next start with B. You can start with any of the remaining symbols, B, D or G. So I have decided to start with B. B to C, C to D, so B to D. D to F, F to G, D to G, G to A to B, so G comes back to B. So these are all the possible squares of the elements in S6, or more strictly speaking, all the possible types of cycle structures that the squares of the elements in S6 can have and will have. Okay. So what are the things that we have got? See, we have got identity, fine. The next one is also identity. We have got a 3 cycle, okay, and from this calculation you can see that in fact any 3 cycle is a square, and which is something we also previously got in the previous solution. Then we have got a product of 2 disjoint 2 cycles. Then we are also getting all the 5 cycles, okay. Next, here also we are getting 3 cycles, so nothing new. This is again giving me identity. This type of squares is giving me what? Again, see, same type of element. Then this type of square is giving me again another such element, a product of 2 3 cycles, again a product of 2 3 cycles, and finally squaring a 6 cycle also again gives me a product of 2 3 cycles where they are disjoint. Okay, now looking at all these element types of the squares, can you think of an element in A4 or sorry, not A4, A6, the alternating group of degree 6? Can you think of an element which will not have one of these cycle structures? That is rather easy now. So we see that the permutation this part I can just simply erase, at least this line. Is in A4 but not in H. Is it true? This is clearly not an identity. In fact, it's a product of a 4 cycle and a 2 cycle which are disjoint. Do we have any such square? Identity? No. 3 cycle? No. So we need a 4 cycle. We do not see any 4 cycle here. Here we are getting a 5 cycle. Then here again a 3 cycle, again identity. See, this is the type of element that we have chosen. However, squaring this gives us what? This. Again an element of this type. This type of square gives us again an element of that type. Again no 4 cycle, no 4 cycle. So among the squares this element is not there, but it is an even permutation. Again I have written A4, A6 sorry. Why is it even? That is because it's a product of 2 odd permutations. One of them is a 4 cycle and one of them is a single 2 cycle. A single 2 cycle by definition is an odd permutation, and a 4 cycle is odd because the length 4 is even, and we know that the product of 2 odd cycles is 2 odd permutations is an even permutation. So that is why this is even, due to which it belongs to A6, but of course it does not belong to H, and that is why A6 is not equal to H, or the same thing, H is not equal to A6. So you can now just simply write, hence so in this type of problems what we are seeing is that most of these problems, the actual permutation does not really matter, but rather what matters is its cycle structure. So that way you can just simply look at the types of cycle structures involved and work with them. It reduces the labor also. So H is not equal to S6, and that is the solution. And let's now see the next one. Just give me a moment. Determine integers in. Integers or the integers. Let me throw in the integers in for which again we have a set H, but this time H is something else. It's the set of those permutations in AN, the alternating group of degree n, whose squares all equal the identity. By epsilon, in this book, the author means the identity permutation is a subgroup of AN. That is, as now n is also changing, okay, and we have to determine those positive integers n for which this subset of AN is a subgroup. Solution. We have, so now we are going to write some some H values for the first few n, first 4 n in fact. Alpha belonging to A1, alpha square equal to identity is equal to identity. Let me first write these things and then I will justify. This is also identity. This is also identity, but the next one is not identity. It is equal to it turns out that this set has these elements, these permutations. Have to be very careful with the commas. A comma at a wrong place will change the meaning of these symbols entirely. I wanted to write 2, 3, but it does not matter. Same thing. Okay, so let us now justify these things. What is A1? We do not usually think of S1 or A1 because when n is 1 or 2, the symmetric group Sn is not really interesting. We only consider Sn from n equal to 3, but still S1 and S2 also exist. What is S1? S1 is the set of all permutations of the single symbol 1, and there is only one such permutation which sends 1 to itself, because there is no other symbol at all. And so S1 consists of only that permutation, which is definitely the identity, and that identity of course is also even. So A1 is this, and so the set of elements in A1 whose squares equal the identity is also just that. So that's how we have this, and this is definitely a subgroup of A1. In fact, it is A1 itself. Okay. What about S2? S2 is the set of permutations of these two symbols 1 and 2. It seems I have a difficulty of writing this other curly bracket. Okay, now it's okay. Now here there are two permutations. One of them is the identity which sends 1 to 1 and 2 to 2, and the other one is the other one, that is which sends 1 to 2 and 2 to 1. This 1 to 2 and 2 to 1 is the 2 cycle 1, 2. It sends 1 to 2 and 2 to 1. And this one is your identity, epsilon. Among these two, this is odd by definition because it's a single 2 cycle. But this is even. So just like A1, A2 also is simply this. And the only element it has also has its square equal to itself. So that is why this set is also the trivial group. It's a group, nevertheless it's a subgroup of A2, and it is also equal to A2. In fact, A1 and A2 are the same thing. Well, actually strictly speaking not the same thing, because this epsilon strictly speaking is not equal to this epsilon. This epsilon is a mapping whose domain is this singleton set 1, and there it's the identity mapping. This epsilon is the identity mapping on this set. However, still they are similar. Okay, now what about A3? We already know what S3 is. S3 consists of these elements: 2, 3, 1, 2, 3, 1, 3, 2. This is our S3. We can get rid of this other parts, right? Otherwise it will be too cluttered. So this is our S3. Now among these elements, what are the even permutations? These three are odd because each one of them is a single 2 cycle, but these are even permutations, this and this. And A3 consists of these 3 even permutations. One of them is the identity and the other 2 are these 3 cycles. But when you take squares, the squares of the 3 cycles are not identity. In fact, the square of any one of them is the other. Only the square of the identity is the identity. So A3 is also just this, and so this subset of A3 is also just this. So this is justified. But what about this one? We can say what the elements in A4 are, or rather what their the cycle structures are. A4 has three types of elements. One of them is of course the identity. Another one is of this type. These three elements that you see, each one is a product of two disjoint two cycles. And there are some other elements which are all the three cycles. For example, this one, or for example 2, 3, 4, and many more such. However, just like these squares, when you take squares of any one of these three cycles in A4, you are not going to get identity. However, epsilon square is epsilon, and when you take the squares of these elements, then you of course get identity. And that is why in this case, this is the set, I mean the set H that we have in the exercise. And it turns out that just like the first three, this is a subgroup of A4. How? The reason for that is that this set, one can verify directly, is closed within itself. If we take any two elements, any two permutations from this set, take their product, it's going to again be an element in this set. But we just simply write like this: each of the above sets is a subgroup of the corresponding alternating group. But when our n value exceeds 4, when it becomes at least 5, then for any such n, the H is not a subgroup. It's never a subgroup. Now let n be at least 5. Then the element, right? The two elements are there which are going to belong to H, but their product does not belong to H. 1, 2, 3, 4 and 1, 2, 3, 5. Yes. Then 1, 2, 3, 4 and 1, 2, 3, 5 belong to H. Why do they belong to H? H means H for this n, okay, this n, this H. And why do they belong to H? Because just like these are elements whose squares equal the identity, here also you can see simply that because the cycles are disjoint and each is a two cycles, so the square will get distributed over the cycles and each square then will be identity, so ultimately it becomes identity. So that's why both of them belong to H. However, their product does not belong to H, which is why H fails to be a subgroup of AN. So now the only thing we have to do is we have to calculate the product. But one, 2, 3, 4, 1, 2, 3, 5. To simplify our calculation, you again use the fact that disjoint cycles commute. So 3, 4 commutes with 1, 2. They are disjoint, there is no common symbol. So you can write 1, 2, 3, 4. And these two vanish because the square of a 2 cycle is identity. And what do we get from this one? So, we have to of course start our calculation from that side. So this one takes 3 to 5 and then that 5 is unchanged by this one. So 3 goes to 5. 5 goes to 3 and then this one takes that 3 to 4. So 5 goes to 4. This one does not change 4. This one takes 4 back to 3. So this is a 3 cycle. And we already know that the square of a 3 cycle is never identity. So this does not belong to H. Hence, H is not a subgroup of AN. So only for those first 4 values is H a subgroup of the corresponding alternating group. For these other higher values, no H is a subgroup of AN. And so that's just it. And that's the solution, and let's just end the video here itself. In the next Gallian update involving group theory, we are going to solve more exercises. I think we will need 2 more Gallian group theory updates in order to complete this permutation exercises, and then we can go to the next chapter. So that's just it for tonight. So I wrap things up with this, and tomorrow of course we have analysis. So see you tomorrow with real analysis. Tomorrow we are going to start a new section. So until then, this is me, Lucifer, from a mathematical room. Have a nice night.